Welcome to analysis of a mixture. So, the absorbance of a solution at any wavelength is the sum of the absorbance of each species in solution at that wavelength. So we have A, the total absorbance of our solution, is equal to the molar absorptivity of the first species X times path length B times the concentration of our species X plus the molar absorptivity of species Y times path length times the concentration of species Y, and so on for each species in solution. Thus, if we know the spectra of each of our components, then we can split our spectrum into a mixture of the spectra of each of its components. So, for example, we can use this method to measure the concentration of acidic and basic forms of an indicator. So, combining this with the Henderson-Hasselbalch equation then allows us to make pH measurements using a spectrophotometric experiment. So, if we have a mixture of X and Y, then we're going to have one of two cases. Either the spectra will overlap significantly everywhere, like we have here in the top case, or there are wavelengths where one species absorbs significantly where the other one does not, as in the bottom case here. So, in the top case, we have both X and Y are absorbing significantly across the whole range that each one of them absorbs in. But on the bottom one, X and Y absorb significantly over here towards the left, but X absorbs more strongly here in this range where Y does not absorb very much, and Y absorbs strongly over here where X does not absorb very much. So in our first case, this top graph here, we need to model the measured spectrum mathematically using some sort of spreadsheet software like Excel. In the second case, the bottom case here, we can make measurements at our wavelengths, one wavelength here and the other wavelength there, where X and Y make the majority contributions respectively. If our spectra are well resolved, then we can solve two equations to find the mixture concentrations. Now remember that the absorbance at some wavelength is the sum of the absorbance of each component at that wavelength. So if we have X and Y, then we can say that the absorbance at wavelength 1, where we have A single prime, is equal to the molar absorptivity of X at that wavelength times the path length times the concentration of X plus the molar absorptivity of Y at that wavelength times the path length times the concentration of Y. And then we can say that the absorbance at that second wavelength, so A double prime, is equal to epsilon X double prime, so this is the molar absorptivity of X at this second wavelength times the path length times the concentration of X, and so on for Y. Note here that you have to measure the molar absorptivities of X and Y separately. Solving the above equation then gives us these two fractions, and note that in the numerator and denominator of each fraction we have this determinant. So a determinant is a shorthand method for writing something like this. So if we have our determinant where we have A, B, C, and D, that means A times D minus B times C. So if we go back, that means that in the numerator here we have our absorbance at our first wavelength times the molar absorptivity of Y at our second wavelength times the path length minus the molar absorptivity of Y at our first wavelength times the path length times the absorbance at our second wavelength, and so on for our other determinants here. So we can extend this same method for more complex mixtures with additional components. We just need the absorbance at n wavelengths for a mixture of n species. So if we have 3 species, we need 3 different absorbance measurements at different wavelengths. If we have 10 different species in solution, we need absorbance measurements at 10 different wavelengths. If you have an absorbing species X that reacts to form absorbing species Y, as you might see in an indicator upon changing the pH, and the spectra of pure X and pure Y cross each other at some wavelength, at any wavelength, then every spectrum that you record during the reaction will cross at exactly that same point. And this point is called an isosbestic point. So we have an example of an isosbestic point over here, where we have various spectra. We've got this blue spectrum ranging all the way to the red spectrum. And so note here that we're going from an absorbing species that absorbs strongly over here to an absorbing species that absorbs strongly over here. Now, at this point, all of our spectra are crossing, so that is our isosbestic point. Note here that the presence of an isosbestic point is very good evidence that there are only two principal species. This doesn't guarantee that there are only two principal species, but this is good evidence that there might only be two. So this works because molar absorptivity for the two species are equal at that wavelength, so at our wavelength here. And this means that the total absorbance at that wavelength doesn't change as one species is converted into another. So if we look at this other wavelength over here, lambda 2, as we go from one spectrum, like this blue curve, down to the red curve, we're changing from one species which is absorbing very strongly at that point to another species which is not absorbing much at all. But at this point, both species are absorbing exactly the same amount. They both have the same molar absorptivity. So when we change from one to the other, we're not changing the total absorbance. That was analysis of a mixture.